Hi, in this video we are going to solve the traveling salesman's problem or TSP using a dynamic programming approach. In an earlier video we have already discussed the TSP and how to solve it using a brute force approach. I will highly recommend you to watch that video first before watching this. The outline of this presentation is going to be like this. We will quickly recap the traveling salesman's problem or TSP, and we will see an example to the TSP problem, and we will also quickly revisit the brute force approach for solving the same, and then we will come to the dynamic programming approach for solving the TSP problem, and finally we will also do a time and space complexity analysis of the same. So let us quickly revisit the TSP problem. So given a list of cities and some metrics between them, it can be distances, it can be time, it can be cost, etc. So or anything which can be imagined as the cost between each pair of cities. So given such a matrix, our goal is to find the shortest possible route that visits each city once and then returns to the origin city. This is an example of a TSP problem represented by a graph, and its cost matrix is also indicated here. So as you can see, the cost from 1 to 2 is 10. So you can see the cost from 1 to 2 here, it is represented as 10. Similarly, cost from 2 to 3 is 4, which is represented here. 2 to 4 is 10. 2 to 4 is 10, which is represented here. And the cost from 4 to 3 is going to be 9, which is represented here. This is just a recap of how we can solve the TSP problem using a brute force approach. The steps were like this. Consider city 1 as the starting and ending point, and then you can possibly generate all the n-1 factorial permutation of routes. So once n-1 factorial permutations are generated, you can calculate the minimum cost permutation from that. And then once you have calculated the minimum cost permutation, then you can return the minimum cost. So essentially, you need to calculate all the n-1 factorial permutations and then find the minimum from that. So the time complexity will be theta of n factorial. So theta of n factorial becomes very large when the value of n is considerably large. For example, if the value of n becomes greater than, say, 12, n factorial becomes very large, and for a typical computer it will take months or years to calculate the shortest keep track of the to find the minimum cost permutation. So using a brute force approach is fairly impractical for real-time problems, for dealing with real-time problems. Now let us discuss about the dynamic programming approach for solving the TSP problem. So the dynamic programming approach algorithm has a slightly better complexity than the brute force approach. It has a complexity of n square into 2 raised to n, which is slightly better than the n factorial complexity of the brute force approach. And in a typical computer, we can solve TSP problems which are having n less than 32 without much delay. So the dynamic programming approach can extend the range of n to, say, 31. And beyond 31, the dynamic programming approach also takes months or years of time to solve. So this is also not a very practical algorithm for dealing with TSP. Now let us try to understand the dynamic programming based algorithm based on a tree-based illustration as shown in the figure. This figure will help us to understand all the possible different routes starting from city 1. Assuming that the starting city is 1, then you have 3 options to be followed with. You can either go to city 2, 3 or 4. And now if you have taken this path, that is the path from 1 to 2, then you have two other choices. You can either go to 3 or go to 4. Suppose you have taken this path, then the only left out city is 4. Suppose you have taken this path, then you have the left out city is 3. Now in this case, here you have already taken 1 to 3. So you have two more possibilities. You can either go to 2 or 4. If you have taken this route, then you are left out with 4. And if you have taken this route, you can go to, now the only left out city is 2. Similarly, here, if you have taken this route, you are left out with 2 and 3. And if you have taken this route, you are only left out with 3. And in this path, you are only left out with 2. Now our goal is to find the minimum cost path from vertex 1 or the city 1. And if you want to find the minimum cost path starting at vertex 1, then it will be possible to find it if you are already aware about the minimum cost path from 2 to the rest of the vertices, and the minimum cost path from 3 to the rest of the vertices, and the minimum cost path from 4 to the rest of the vertices. And similarly, if you to calculate the minimum cost path at 2, it will be better if you already know the minimum cost path at this 3 and this 4. Similarly, to calculate the minimum cost path at this vertex 3, it will be easier if you are already aware about the minimum cost path at 2, this 2 and this 4. And similarly, here calculating the minimum cost path via 4 becomes easy if you are already aware about the minimum cost path via this 2 and this 3. And this definition is going to be recursive. So it essentially means that if you want to calculate the minimum cost path at this level, you should know the minimum cost path of the vertices in the next level. And to calculate these minimum cost paths in this level, you should be aware about the minimum cost path in this level. And similarly, this definition is going to be recursive. So we can observe that both memoization and recursion need to be applied to solve this problem. And if you apply memoization and recursion, you are actually applying dynamic programming. Memoization is required because in each level you want to know about the min costs from the previous level. And recursion is required because this definition is going to be recursive until you are left out with no more vertices to visit than one. So the idea here is to start from bottom level and then calculate the min cost at each of these nodes and then go to the higher level. So once you go to the higher level, since you are already aware about the min costs at a lower level, then it becomes easy to calculate the min cost at that level. And then you do this recursively until you get back to city 1. Now let us visualize how dynamic programming works in our example represented by this graph. Also note that the vertex 1 is added at the end of every other vertices to indicate that you have to get back to city 1 once you have traveled through all other cities. Now we can calculate the min costs at each level starting from the bottom level. So here at node 4, the only vertex remaining to be visited is the origin vertex. There are no other intermediate vertices to be visited. This is true for all the nodes in the last level. So we can actually directly look at the cost matrix and write the distance between the vertices For example, in the case of 4, you can look at the cost matrix and see that the distance from 4 to 1 is 8, and it is the minimum cost of going from this level to 1. Similarly, for going from 3 to 1, the minimum cost is going to be 6, and the minimum cost, again it is 4 to 1, that is going to be 8, and the minimum cost for going from 2 to 1 is going to be 5. The minimum cost for going from 3 to 1 is going to be 6, and the minimum cost for going from 2 to 1 is going to be 5. Now let us go to the level above and find out the minimum costs of each of the nodes in that level to reach back to the vertex 1. If you take the node 3, then to get back to node 1 or the city 1, you have to pass through only one intermediate city, which is 4, and the min cost of 4 is already calculated. So based on the min costs at the lower levels, we can calculate the min costs of each node in this level. So let us calculate it one by one. To calculate the min cost at this node, that is node 3, the only thing that we need to do is to add the distance from 3 to 4 to the min cost at 4, which is already calculated as 8. So the min cost at 3 will be distance from 3 to 4, that is 12, plus 8. So it is going to be 12 plus 8. And the min cost from this vertex, which is 4, this 4 is going to be the distance from 4 to 3. 4 to 3 is 9, so it will be 9 plus 6. And the min cost from this node 2, is going to be the distance from 2 to 4, that is going to be 10, and 10 plus 8. And the distance, the min cost of going from 4 to the origin node will be 4 to 2 plus min cost at 2. That is 4 to 2 is going to be 8. So this is going to be 8 plus 5. And similarly, at 2 the min cost will be 9 plus 6. At 3 the min cost will be 13 plus 5. Now let me add all these values and write their sums. So the sums are 20, 15, 18, 13, 15 and 18. Now we can go to the upper level and calculate the minimum cost at each node. Note that in this level you have two choices for reaching to the origin city 1. For example, if you are at 2, there are two choices for reaching to the origin city 1. One is 2, 3, 4, 1, that is this path, 2, 3, 4 and then 1. The other path is 2, 4, 3, 1, that is 2, 4, 3, 1, this path. So while calculating the minimum cost, you need to choose the route having the minimum cost. In this case, if you take the route 2, 3, 4, 1, then the cost will be the distance from 2 to 3. The distance from 2 to 3 is 9. So 9 plus the minimum cost at 3, that is 20. This is one option. Another option is that you can go through the route 2, 4, 3, 1. In that case, the cost would be the distance from 2 to 4, 2 to 4 is 10. So it would be 10 plus the minimum cost at 4, that is 15. So the min cost at 2 will be the minimum of these two. It's going to be the minimum out of these two. Let me write minimum. Minimum of 9 plus 20, comma 10 plus 15. That is minimum of 29, comma 25, which is nothing but 25. Now you can pause the video for some time and calculate the minimum costs at all the vertices. Hope you are getting the answers like this. At vertex 2, you are actually calculating minimum of 29, 25, which is 25. At vertex 3, you have to calculate the minimum of 31, 25, which is again 25. And at vertex 4, you have to calculate the minimum of 23, 27, which is 23. Now we are only left with the origin city located at node 1. Node 1, we can have three choices. We can either choose the route through 2, that is this route, or we can choose the route via 3, that is this one, or we can choose the route via 4. And the min cost at node 1 will be the minimum of all these three. So we can comfortably write this as min of. So the distance from 1 to 2 is going to be 10. So 10 plus, we are already aware about the cost at 2, which is 25. That is 10 plus 25, comma. We want to calculate the cost of the path via 3 now. It is going to be distance from 1 to 3. 1 to 3 is 15. 15 plus 25, comma. Now the cost via 4 is going to be the distance from 1 to 4, that is 20. 20 plus 23. So it can be written as 20 plus . So the minimum among all these will be 10 plus 25, which is 35. So the min cost from city 1 is going to be 35. Let me write it here. This is going to be 35. So we are done with our ultimate goal of finding the min cost from city 1, and it is found to be 35. Now let me show you how to represent the min cost at each node starting from node 1. Let me zoom this image. So we will start by writing the min cost at node 1, and then we will continue to the other levels. The min cost at node 1 can be represented as g of 1, comma set 2, 3, 4. This means that your starting vertex is 1, and the rest of the vertices that you want to go through is 2, 3, 4. Similarly, we can write the min costs for each of the nodes in the other levels as well. For example, if you are at node 2, the min cost from here it can be written as g of 2, comma the rest of the vertices to be visited are 3 and 4. Similarly, if you are at 3, it can be written as g of 3, comma the rest of the vertices to be visited are 2 and 4. And similarly, the min cost at this 4 is going to be g of 4, comma 3 and 2. Now we can move to the level below, and at this node 3 we can write the min cost as g of 3, comma. So the only remaining vertex here is 4. So it can be written as g of 3 comma 4. Similarly, at this node 4, the min cost can be written as g of 4 comma 3. Now let me fill the min cost representations of all the nodes in this level. Now let us move to the last level and try to represent the min cost representations there. Remember that in the last level, we don't have any more vertices to be visited than the starting city. Here what we will do is that we can write g of 4 comma null set. It essentially means that there is nothing to be visited than the starting city here. So when you are at 4, you don't have any other intermediate vertices to be visited. Similarly, at vertex 3 you can write g of 3 comma the null set, which is represented by 5. We can simply write 5 as well to represent the null set. So here we can write g of 4 comma 5. Similarly, here we can write g of 2 comma 5, and similarly here we can write g of 3 comma 5. We are left with one more vertex here. There we can write g of it can be written as g of 2 comma 5. Now we can define the min cost in a recursive manner. The min cost from city 1, which is our ultimate goal, which is represented like g of 1 comma 2 3 4, can be defined like this. So I can write like this: g of 1 comma 2 3 4 can be recursively defined as the minimum of we know that there are 3 choices which we have done in our example. We can either choose this path or this path or this path. So we have to find the minimum of that. So the recursive definition would be, if I am representing C12 as the cost from going from 1 to 2, then I can write C12 plus, again the min cost at 2 is defined to be g of 2 comma 3 4. So I can write g of 2 comma 3 4 comma, the next way is c of 1 3 plus g of 3 comma 2 4. And there is one more way, that is c of 1 to 4 plus g of 4 comma 3 2. So once you calculate the minimum of this, then you have achieved your result. But for calculating this, you should know what is g of 2 comma 3 to 4, g of 3 comma 2 to 4, g of 4 comma 3 to 2, and that's why this definition becomes recursive. In the next slide, we will be representing all the min costs and then try to analyze the time complexity. Now that we have a reasonably good understanding of how to solve a TSP by using the dynamic programming approach, we can try to analyze its time and space complexity. But before doing so, we should be able to write a recursive definition for a TSP problem. Before writing this formal recursive definition, let me try to explain how this can be used in our example. Remember that in our example, we were dealing with a 4 vertex problem. When we are at vertex 1, we know that we have 3 more vertices to be visited before getting back to city 1. And similarly, when you are at level 2, that is in this level, then you have 2 more vertices to be visited. And when you are at in the next level, then you have 1 more vertex to be visited. And when you are in this last level, it is obvious that you don't have any more vertices to be visited. Now we want to establish a formal recursive definition for the min cost. Before doing that, let me define the recursive definitions of min costs at each level, starting from the last level. The min cost definitions of the last level are as shown here. We know that in the last level, we only need to get back to the origin city 1. So the min cost can be directly accessed from the cost matrix. For example, the min cost from the node 2, which is represented as G2, 5, is nothing but C21. The min cost definitions of the second last level are as shown here. For example, G23 can be calculated as C23 plus G3, 5. Note that we are using the min costs calculated in the previous level here. Now the recursive definitions for this level can be calculated as shown here. From this level onwards, we have more than one route for getting back to city 1. So while calculating the min cost, we need to find the minimum cost route from the available routes. For example, while calculating the min cost G2, 3, 4, you have two options. You can either take this route or this route. And you can see that in our expression, we are finding the minimum of those. That is, either you can take the path C23 plus G3, 4, or you can choose the path C24, G4, 3. And so the min cost will be the minimum of those. Now the recursive definition for the first level, which in fact is our ultimate goal, can be defined as shown here. Note that here we have three choices. You can either take this path or this path or this path. So you have to find the minimum of these three paths. So you can see that we are calculating the minimum of three different paths represented by C12 plus this quantity, C13 plus this quantity, C14 plus this quantity. We have already seen the definition for min cost from level 1, which is defined like this. The function shown here indicates the minimum path length from starting city 1. Now we can write this definition in a more formal way as g of 1, set of all vertices v minus the vertex 1, which is the starting city, equals the minimum of k going from 2 to n, k less than or equal to 2 less than or equal to k less than or equal to n, c of 1k plus g of k, set of all vertices v minus the set 1, k. It can be verified that this expression holds for our current example and any given example with any number of vertices. Note that this expression is for finding the min cost from starting city 1. Now we can generalize this expression for any starting vertex by writing g of I, s, where s is the subset of all vertices yet to be visited, equals the minimum of all j belongs to s, c of ij plus g of j comma s minus j. It is evident that our subset S will not contain 1 because 1 is the starting city. So 1 will not belong to the subset S, and also whenever you calculate a GIS, that particular I also will not be a part of the subset S. Let us call this as equation 1 and this one as equation 2 to refer in our further explanations. Now we are very much ready for the time complexity analysis. It is clear that we have applied a bottom-up approach to solve the TSP problem by calculating the min costs at each level. Then we stored it and used it in the higher levels. Assume that the min costs are stored in a linear way using an array like this. Then we will have to calculate and store the min costs values of all the GISs in this array before finding the ultimate min cost. For example, the values to be stored can be represented as the array starts with the value g of 2, 5, then g of 3, 5, and so on up to g of n, 5. Note that all these min costs are min costs when the number of vertices yet to be visited or the subset size yet to be visited are 0. That means the size of the subset in all these cases is going to be 0. Similarly, you have to calculate the min cost when the subset size is 1. So these are the values when the subset size is 1. And this has to be continued. You have to also calculate when the subset size is 2, and so on until the subset size becomes n minus 1. That is the last case. That is g of 1, 2, 3, 4 up to n. So in this case, the subset size is n minus 1. So all these GIS values has to be calculated and stored in a linear data structure so that the final min cost, which is this one, that is g of 1, 2, 2, 3, 4 up to n, can be finally calculated. Now it is evident that the time complexity depends on the number of GIS to be calculated and the time required for calculating each of them. Let us assume capital N as the number of GISs that have to be computed before calculating the final min cost, that is g of 1, 2, 3, 4 up to n. So capital N refers to this number, the number of GISs to be calculated before calculating the final min cost. It is possible to estimate the value of n by counting all the possible GISs that can be written. And it can be calculated if you know permutations and combinations and set theory. In the sense, we need to write all the different sets combinations of GISs possible, and we will be able to estimate the number of GISs written in such a manner. That means whenever you write GISs, you are going to write a quantity here and a quantity here. And we know very well that this quantity always have a range starting from 2 and going up to n. So the total possible combinations of writing the first quantity is going to be n minus 1. Total possible ways of writing the first quantity is going to be n minus 1. The second quantity will be equal to the number of subsets having size 0 plus the number of subsets having size 1 plus the number of subsets having size 2 plus etc. plus the number of subsets having size of n minus 2. And we know that always we are not considering that our subset will not contain 1 and I. So total number of possible values is going to be n minus 2. So this sum can be written as n minus 2 C 0 plus n minus 2 C1 plus etc. plus n minus 2 C n minus 2. So this can also be written in a summation form as sigma of k going from 0 to n minus 2 n minus 2 choose k, and k here refers to the number of elements in the subset. K is going to be the modulus of S. So it can be easily identified that this quantity is nothing but 2 raised to n minus 2, because this is nothing but the number of subsets of a set having size n minus 2. So the total number of GISs that are to be calculated is going to be a product of n minus 1 into 2 raised to n minus 2. So capital N is going to be equal to n minus 1 into 2 raised to n minus 2. And we can also see that the size of this array is going to be of the order of this quantity, that is n minus 1 into 2 raised to n minus 2. Now, to estimate the time complexity, to have an estimate of the time complexity, we also should take note of the fact that the computation of GISs with a size capital S is equal to K, the modulus of S is equal to K, requires K minus 1 comparisons. And the value of K can be at most n minus 2. So the complexity will be of the order of so you need to have n iterations. So n square into 2 raised to n. And the space complexity is going to be of the order of n into 2 raised to n. It's going to be of the order of n into 2 raised to n, which is nothing but a measure of the size of this array. So two things you need to remember: the time complexity of TSP is using dynamic programming is the order of n square into 2 raised to n, and the space complexity of TSP using dynamic programming is of the order of n into 2 raised to n. Now, as an assignment, you can find the min cost from the given graph represented in the form of a matrix. So you have to start writing from g of 2, 5. You have to find g of 2, 5, g of 3, 5, g of 4, 5, and similarly all these values, and finally we'll have to find g of 1, 2, 3, 4. I have taken a lot of time and effort in creating this video lecture just because of the fact that TSP is one of the classical problems in algorithm analysis. And we have looked at a method of solving TSP problem using the dynamic programming approach. And people have came up with many different heuristics based approaches to solve this problem. And they have tried to reduce the time complexity and have obtained solutions which are very close to the optimum solutions. And since this is an open problem in research, you can also try to contribute some heuristics based approaches to solve the TSP problem. Thank you.